All right, everyone. Thanks so much for coming out to AGI House San Francisco on a Saturday and joining Saturday Robotics. My name is Julius. I get to host events and run the community here at AGI House San Francisco. We're super stoked to have Saturday Robotics here for the very first time, hopefully not for the last time. So yeah, quick round of applause for you guys showing up here on a Saturday. That's awesome. So a bit of context. Don't be put off by the green on my shirt. Turns out that being a bit creative on the weekends actually helps. So this is some all color. But otherwise, we try to keep this place super clean. So what that means is, in case you would be so kind to not leave any of the strawberry straws on the floor and put in the end of the day some of the snacks back in the trash can, that'd be wonderful. Now, where are you right now? AGI House was originally started in the South Bay, Hillsborough, in 2022 as Neogenesis by Andre Karpathy and Jeremy Nixon, who lives upstairs. And the idea was to bring together the greatest researchers and inventors to build AGI. Now, AGI is nowadays symbolic for really impactful deep tech companies that can help accelerate humanity's trajectory, right? And so, in many ways, over the last 4 years, we've succeeded with that mission. We've had 10 unicorn founders come directly out of the house as roommates, and 9 more center $1 million company founders. Companies like Perplexity was started at one of our hackathons. Lovable founder Anton lived with us last winter, right? So we would love this place to continuously be the technical nexus for the best founders and researchers and produce great inventions. Now, on the frontier of robotics, there's a lot of incredible stuff happening. I'm sure you've all seen the launch video from 2 days ago. Who knows what I'm speaking about? What is it, 25 degrees of freedom? Exactly. So incredible stuff is happening in the space. The whole VLA space is exploding. So we're super stoked for you to be here and hope that some of that spirit that we've been catalyzing in that house maybe inspires you to yourself start independent research, start a company in the space, think a bit bigger on how your work in robotics can accelerate humanity. And yeah, you're all going to be on our newsletter. And you can, of course, unsubscribe, but in a good case, you're going to learn about more interesting events. In a great case, you're going to come up to me at some point or send me an email and be like, hey, Julius, I have a reading group on longevity technology, or on mechanistic interpretability, or on an interesting deep tech topic, and I would love to bring a community to the house. And so we love to support this. For reading groups, we don't charge anything, because we're we want to see this happen more in the world. So yeah, come talk to me, come find me, come send me a message. My name is Julius Ritter. Find me on LinkedIn or direct my number. And yeah, it's a pleasure to have all of you here. And now let's give it up for, first of all, Jun Fan for organizing this, and also our speaker, Kwan Lu, who's going to present today. Thank you so much.
Yeah, thank you so much, Jun Fan, for organizing this kind of event. And thank you for having me today. So my name is Kwan Lu. I'm currently the postdoc at Purdue University, and I'll be also incoming assistant professor at EC in the University of Nebraska-Lincoln. And today, so I would like to share my thought on how to achieve the safe and general purpose robots through the self-Tactile-Centric multimodal intelligence. And yeah, let's start by looking at how robots have evolved over the last few decades. So in the past, robots mainly work in factories. For example, robot arms in car manufacturing. So the system were isolated from humans and highly structured. So moving forward, so we see systems like Amazon warehouses, mobile robots move around for logistic tasks. So the environment are more dynamic, but still relatively structured. So now robots are moving toward unstructured, dynamic environments. So in these settings, so robots must handle uncertainty, dynamic changes, and context-rich interaction. And this requires robots that can interact safely and intelligently with objects and their surroundings. And recently, we have seen impressive demonstrations humanoid robots powered by like large AI models can perform complex tasks in factory settings and even in home environments. So for example, robots like Atlas from Boston Dynamics or Unity G1 here. So these results are very exciting. So, but this also raises an important question here. So have large AI model like a really solve robot manipulation? So I believe like the answer is no. So there's still like many challenges that we as roboticists need to solve before robots can really deploy reliably in the real world. So for first, context-rich manipulation is still like difficult. Many tasks that require very high precision, sometimes at a sub-millimeter level. For example, a gear assembly robot can still fail to complete the task. A second challenge here is that so handling fragile and delicate objects is still challenging. Robot may damage or break objects during manipulation. And finally, safe interaction with human remains a major concern here. Robot needs to operate safely in the shared environment. So to address the challenges, so I believe that tactile sensing and soft robots bodies can be the key enablers here. So most current research focuses on improving robot intelligence, but in contrast, my research focuses on both hardware and computational intelligence. So on the hardware side, so I developed novel tactile sensing devices for robot bodies. On the intelligence side, so I integrate tactile sensing with learning and control to enable more robot operation. So overall, I believe that combining new robot hardware with advanced intelligence is a promising path toward safe and general purpose robots. So this experiment shows how important tactile sensing is for reliable manipulation. For example, on the left, so with the normal tactile feedback at the fingertips, the subject can easily lie the mesh and smoothly. On the right, when tactile feedback at the fingertips is removed, so the task becomes more difficult and less precise. So although the subject can still complete the task at the end, but it takes much longer and requires more effort. So this highlights how critical tactile sensing is for reliable manipulation. So with that, so I would like to briefly introduce my research that I have done so far. So my work combines a development of tactile sensing hardware with learning and control intelligence here, and together these two layers enable a wide range of applications. So include context-rich manipulation, human-robot interaction, and deployment across different robotic platforms such as mobile and aerial systems. So first, I will focus on the hardware layer here. So in this part, so I will briefly introduce the vision-based tactile sensing technologies for robotic links, which can also be applied to the sub-continuum systems. So I also developed multimodal sensing systems that integrate tactile and proximity feedback into the self-robot body. And I will show several examples of this work, including methods for contact detection, deformation sensing, and multimodal for sub-robot bodies. And next, I will focus on a learning and control layer here. So in this part, I first show how tactile sensing can be integrated into the control framework to enable safe and adaptive behavior during contact with external environment. And I then introduce my recent work on multimodal robot learning with supervised learning or imitation learning that integrate vision and tactile sensing modalities simultaneously. So the goal is to demonstrate how tactile feedback can enable more robust and adaptive manipulation in certain contact-rich environments. And finally, I will present several examples to show how my research can be expanded to a wide range of robotic applications such as mobile and aerial systems. So let me start by showing some examples of my tactile sensing hardware designs. So I will briefly introduce conventional tactile sensors. So conventional tactile sensing principles usually come from capacitive, piezoresistive, piezoelectric, and so on and so forth. So each of these has been widely studied and used, but they all face some problems. So first, the design and fabrication are often complex and expensive. Second, they have limits in spatial resolution and consistencies. And third, the wiring can be bulky and hard to integrate in the real robotic systems. So to address the issues, many groups, including my research, have turned into a new direction. So it's called like vision-based tactile sensing. And here are some examples of vision-based tactile sensors that researchers have developed around the world. So now I will show like the vision-based tactile, how the vision-based tactile sensor works. In principle, the sensor consists of like the internal camera here and the sub-elastomer shells here. And when there is like the contact, like in the surface area, like the camera here can capture this deformation of the skin, and from that we can infer a wide range of tactile information. For example, here you can see the sensor can capture the contact geometries of the objects, and if like there's markers embedded in like the sensor skin here, the sensor can also track the displacement markers, and from that it can infer like the 3D shear force information. And for example, here you can also see that the sensor can also like estimate the pose of the object that comes into the contact with the subskin here. And so this slide shows how like vision-based tactile sensing devices can be classified based on their size and the number of sensing modalities that they offer. So previous studies have mostly focused on small size devices, which are typically like designed for robotic fingers. My work like focuses more on like developing large area vision-based tactile sensing devices for whole body like robotic links. So these type of sensors can be used for human-robot interaction as well as for safe interaction with the surrounding environment. And so now we should introduce the designs of this like large area vision-based tactile sensing device, which we call like the tackling. Similarly, we also have like the two cameras attached at the two ends of the link here, and inside the subskin here we have like the markers like embedded, and here's like the image view that we can capture from the internal camera here, and from that we can use a CNN model to process like the image here, and from that we can infer like the contact depth or like the contact information across the entire skin surface. And on the right is the real-time operation of the like a tactile robotic links over there. So now the question is like how we can like collect the data sets and train this kind of like neural network or the CNN model here. So similar to like all the data-driven like approaches, so we need a data set for the supervised learning. However, collecting real tactile data at this scale may be difficult. So instead, we build a simulation platform for our vision-based tactile sensing device. So this platform allows us to generate the training data efficiently. It can also simulate realistic skin deformation as well as the corresponding images captured by the internal cameras. So what you can see in this slide is the real tactile sensing device with like the real like tactile images as well as like corresponding digital twin that can be in the simulation environment and the simulated tactile images over there. So now let's take a look at how the simulator is constructed and how we can collect the simulation data to train the tactile models here. So actually at the high level, so we use an FEM like simulation software so to model the subskin deformation, and our physics engines like any like a physics engine like Gazables or like Unity or something to generate the realistic virtual tactile images here, and the data generated from these components is then used to train the tactile network, which is learned to predict the contact information. So, however, when we train like the models with the simulation here, so actually there would be some mismatches between the real and the simulation image that can cause like the models evaluated in the real image is not perfect. So here we are about to use another like a generative model to transform the real image in the real domain into like the image like in the simulation domain that should be similar to the simulation images. And here, so we evaluate the performance of the tactile network on the simulation device or like on the simulated images, you can see that so the prediction of the tactile information is very close to the baseline here. However, like when we evaluate this model on the physical device that have the real images here, as I mentioned, there is like difference between the sim and the real domains. So actually the prediction is not perfect and doesn't align with the baseline information. And so the inaccuracy here, so let's see how we can like solve this problem. And so this inaccuracy it can be explained by the mismatch between the real and the sim here. So we propose to use another like generative. Here we use the GAN model like that is trained to match like the image in the real domain to like the simulation one. And so we can see here, so by passing these real images to the trained narrative model to map like the image in the simulation to the real domains and to the simulation domain, and from this we pass the input in the simulation domain to the tactile network here, and actually the performance of the prediction of the tactile information can be recovered like using this method. And here we showcase the performance of tactile sensing in real time. So actually we can run this model like quite effectively, and the sensor skin here can predict like the contact location as well as the contact intensity across the entire skin surface. And not only the sensor can predict the single contact, it can also predict the multiple contact location as well as the contact intensity at the same time as well. So far I have presented like our approach to enable the large area vision by tactile sensing for soft robotic links. And actually there is one dimension is like how we can integrate different sensing modality into this soft tactile link, right? For example, there are several works they try to integrate the proximity sensing into this kind of device to enable a unified like multimodal sensing embodied for this kind of tactile device. And similarly, it's like there's a lot of work that's just focused on enable multimodal sensing for small scale devices, but there is missing some study that focus on the large area vision based tactile device. So therefore based on reverse like tackling device here, so we propose a new vision based sensing device that integrate both like a proximity sensing into a single sub-robotic link, which we call the ProTac here. So now I will introduce like a ProTac, a vision-based proximity tactile sensing technology for sub-robotic links. And as you can see here, so actually on the left-hand side is the tactile sensing mode of the tactile link. Similar to previous like device, so we have the two camera at the two ends, we have the sub-skin, we have the markers, and by capture the image like with the like markers here, we can use the CNN model to predict tactile information across the entire skin surface. However, like the interesting point here is that actually the dark hints here, it can switch the transparencies between the dark to the transparent state. So that's when the skin becomes transparent. So actually the two cameras like inside the link here can see through the external environment like to observe and to predict the distance of the objects that glow at the skin surface. From that it can infer like the distance between the external objects and the skin. And as you can see on the right hand side here is like the view of the camera that is see-through like the transparent skin, and from like the transparent views like that actually we can use the depth model to like reconstruct the external scenes or like to detect like the nearby objects. Yes.
Can you roll back to the last slide? Where is the camera that shows the depth image?
So actually here's like we use like monocular depth prediction network. So here's the camera that can capture the depth image. Here's the camera. First it capture the RGB image, and from the RGB image here, we use the depth model to predict the depth map.
Okay.
Yeah, I will show you like how we can obtain the depth, like depth map here later.
Is it a molecular camera or?
Yes, monocular camera. Actually we have like the two camera here, and actually each camera here can obtain like its own depth map, and actually we can fuse the two information so that we can like obtain more accurate information for the external objects.
Okay.
Yeah.
Did you like have to fine tune it to because of all the markers in between?
That's a very good point. So actually we also have to fine tune like the base depth model here so we can obtain a more accurate depth information, because like when we see through the transparent skin here, they reflection something like that, and it affect like the base depth model a lot. So that's why we have to do the fine tune so that the model can work better.
And the image over there on the top left corner, is this from the same camera?
Yeah, it's the same camera.
Okay.
But you can see like the difference because we have the skin here that can switch the transparencies. It can switch between the dark state, and when the skin is in the dark state, you see the view is like this. And when you switch the transparency to the transparent state, you can see like the view over there.
Okay.
But it's both from the same camera.
Thank
I
you.
have a question.
Yeah.
Is in the dark state, how are the markers lighted up?
Can you say it again?
In the dark stage, how does the markers light up? Like,
Oh, actually, like inside here, we have like the LED system that line up like the inner space of the link here. And when we switch the transparency, we just turn off like the LED, so that it can rely on the external lighting system for the proximity sensing mode. Yeah. Yeah.
So you could also try like IR reflective markers.
No, we don't use that. We just use like the more normal markers. Actually, the marker is made like from the silicone.
Yeah.
It's the same like material with the skin here. Yeah. Any other question? Yeah, and now let's see how we can like enable like the transparency wishings of the skin. And actually here is the design of the link here. And actually the secret here is that we use a soft skin with like the PDLC film. And the functionality of the PDLC film is that actually it can switch like the transparency when we apply a voltage to the skin. And actually here's from like materials development, something like that. Yeah. And so now let's see how we process like post-tactile and proximity information in the Protect. Like in general, like we use deep learning models for this kind of dual perception here. And these models take the images captured by the sensor internal cameras in either the opaque or the transparent state corresponding to the tactile and proximity sensing respectively. And for the tactile sensing mode, so actually we follow the same simulation and learning framework that I introduced earlier, so I won't go into the details anymore. So here, as you can see, it's like the real-time operation of the robotic link in the tactile mode. Similar to the tactile device, it can also like predict the tactile information, for example, the contact location as well as the contact intensities across the entire large area skin surface, as well as it can also predict like multi-bond like contact interaction here. So now I will like briefly introduce like how we can enable like the proximity sensing when the product skin is in like the transparent state. And here's like the overview of the pipeline here. Actually the camera, so we can capture the see-through image from the internal camera here, and we pass it into the fine-tuned depth monocular network here to predict the depth map, depth information, and from the depth information we can reconstruct the 3D point cloud of the external environment, and from that we can obtain the distance between the sensor skin and external like objects like this. And here's like the real-time operation of the depth map reconstruction from the transparent camera view here. And here's like the real-time operation of the Protect link in the proximity mode. Actually, as you can see when the human approach, so the distance closer, so we can see some kind of signals of the proximity sensing over there. Yeah, so now that's it for like the hardware development. So before moving, so early in this talk, so I have mentioned like several challenges in the robot manipulation, such as self-interaction and the contact-rich manipulation. So in this part, so I will show how like the tactile sensing device that we developed can be integrated into the control and a learning frameworks to enable like the safer interaction with the environment, as well as more reliable contact-rich manipulation here. So in the first example, so I will demonstrate how the like the tackling device here can react and to mitigate the impact force during the external contact. So the main objective here is like to enable the robot equipped with the tactile link to move away from the contact regions. So to achieve this purpose, so we model the system as the mass spring damper, allowing the robot to dynamically adapt based on the contact force detected by the tackling. So for the experiment, so we attach the tackling into a robot arm and intentionally move the robot arm toward like the obstacle over there, and let the controller do its task to respond to the impact. And here, so we compare like the reactive performance of the tactile link with the conventional rigid device here, and we see that so the maximum like contact force on the soft link is just around like 2 newtons, which is like a much smaller compared to the contact force observed on like the conventional rigid link, which is around like 60 newtons. So based on this like results, so the tactile link is like very effective in mitigating the large impact forces. And the key takeaway is that like combining tactile robot bodies with the appropriate control strategies, so strong potential for like a safer robotic systems. Yeah.
So this is you're using tactile sensing, so the robots know when to slow down.
Actually, like the robot will know when the contact happens,
Okay.
and based on the context, it's just like enable the reactive behavior to move away from the contact regions.
Okay.
Yeah, actually, because here we model the entire system, the robot system here, like the mass spring damper. So actually, we have like the compliant behavior, the active compliant behavior from the controller, as well as the passive softness from the tackling as well. And by combining these two components, it can enable this kind of reactive behavior of the robot, as well as like reduce the impact force that we observe on the tactile link.
So how do we know if the peak force going down is not coming from the soft material?
Yeah, I mean, like the peak force should be come from the two components, both based on the softness of the link and based on like the reactive of the controller as well. But I think most of the time, like it should like come from like the softness of the link as well as the sensitivity of the tactile sensing on the link.
Okay.
Yeah.
I'm trying to understand the practical application of this. If this arm has anything inside of it, the sensor wouldn't work anymore. Is that correct? Is that the correct understanding?
So you mean this link, if there
It's
is
the cylinder. If there's anything, any metal or any rod inside of it, it will stop working. Is that correct?
yeah, that should be. Yeah, because we need to observe like the markers on the skin clearly if there is anything uploaded there. So I think it's not working.
So your practical application for this would be how hard that can, I mean, what would it be an arm in a robot, or is it I'm trying to understand where you would incorporate this in the robot.
Or actually, like it should be on the arm of the robot. And actually nowadays, like most of the robot arm is rigid. And actually, one of the applications is we just build like a robot arm with a soft skin from scratch. And I think it would be more practical rather than we integrate the current tackling device into the current robot arm.
Okay. So the whole arm would be hollow inside,
Yeah.
basically. And so but the softness of the material would limit the weight that it can lift or.
I see. But actually, like inside the link here, actually we still have the bond, and actually the transparent one. So the transparent bond like doesn't affect the view of the camera at all.
Oh.
So the bond here is like improve the robotics of the link, while the softness of the skin like improve the softness of the interaction.
I have one more question, a few slides before. So the model that you have that basically transforms the images that you get to an accurate, more simulation accurate model. Every time you change material or shape, that has to be retrained. Is that correct?
Yeah, that is exactly. Yeah, it is. Yeah.
Just curious, why not spend a little bit more time on the simulation accuracy to prevent that redo of the work?
Yeah, but I think like yeah, but actually like when we change the materials, actually it's not quite difficult to change the model in the simulation. And when we change the material, I think we can update the model in the simulation and we recollect the data and we retrain the model again. And I think that shouldn't be very difficult. Yeah.
Is there a reliability latency trade-off here? I'm thinking about like these sensors. Yeah, the data is being processed to a CNN or deep learning models, and it communicates to a VLA or robot brain, and then sends actions back. And we're talking about safety applications. Let's say a child approaching a robot very fast. So I was thinking about, is there a trade-off, or if there is, then how do we think about the trade-off?
Yeah, I think that's a very good point here. Actually, for the safety application, I think we need like the high processing speed for both the sensor and for the brain as well. And here actually we focus more on like the sensors, and we observed that so the latencies of this sensor device would like heavily depends on the FPS of the cameras. And actually nowadays, so the cameras we use like can process like up to like 60 or 100 like frame per second. And I think it's kind of enough for this kind of application. But maybe if we want to like enable the robot to react like more faster, I think we need like a different like a processing method to enable like a higher like processing time. And yeah.
So for the soft tactile link, is it slowing down on contact, or is it slowing down when it approaches before contact based on the depth perception?
So actually, it's just like slowing down when it detects the contact.
After contact?
Yeah, after contact, yeah. Okay. So and here, so I'm gonna show like in another like application of like the soft tactile link device, and here we trying to integrate both like the tactile and proximity sensing mode here. And the task here is that so actually we want the robot to reach a target location while like have any like obstacles along its way. And actually, as you can see here, for example, if we have the stippling for this task, and actually when the stippling collide with the obstacle here, it will cause like significant impact force, and the arrows between like the target location will never be like mitigated to zeros. However, if we have the soft link here, so the robot can like mitigate first the contact, and it can also like accommodate the contact here and try to minimize like the location arrow here. And actually here we try to integrate both tactile and proximity sensing, and here we use like a model-based control with like some optimization-based control here for the test. And here's the experiment. For example, the robot is commanded to achieve like the target location. First target location here, and the second target location here, and there is like obstacles along the way. As you can see that, so actually because we have the proximity sensing at first, so the robot can reduce the speed before comes into the contact with the obstacle here. And based on the tactile sensing, when the robot collides with the objects, it can reduce, it can accommodate the contact and navigate like gently into the target location. And you can see here we do the benchmark with and without the proximity sensing here. And actually with like the proximity sensing, because it reduced the speed before getting into contact. So that's why like the contact force is more like stable, and actually we don't see any spike in the impact force here. And so I have like presented like several like examples of how soft tactile sensing link can enable safer interaction with the environment using like the models or like optimization-based control. So now we'd like to introduce like our recent work on like supervised robot learning for more reliable contact-rich manipulation. So recently we have seen like significant progress in policy learning for robotic manipulation, where robot actions are guided by multimodal observation such as vision and tactile feedback. For example, as you can see here, so the robot can perform a wide range of tasks such as chicken handling, chip insertion, cucumber peeling, and facial object handling. So I'm going to skip this. So actually, it's just like the overview of the imitation learning, and I think like most of the guys here are very familiar with this kind of framework. So even though like the imitation learning with the sensing shows very strong promise for like contact-rich manipulation, so a major challenge like remains. So there is currently no standard benchmark. So and we also lack a deep understanding of how tactile sensing affect the policy learning and overall like system performance. So in practice, like different worlds use different training algorithms, model architectures, and sensing configurations. So this makes it very difficult to fairly compare methods and to understand impact of tactile sensing on the robot learning performance. So if we look at like the imitation learning with the visual observation, the situation is very different. There are a handful of reproducible benchmarks in this domain. So they provide shared data set, environments, and evaluation protocols that allow like researchers to directly compare methods and build on each other work. So however, standardized benchmark is still missing for imitation learning with like vision and tactile feedback integrated to each other. So we need to build the same momentum for the visual tactile policy learning. So to fill this gap, so we recently introduced Manifold imitation learning benchmark for contact-rich manipulation. So Manifold provides a scalable and reproducible platform for studying and evaluating visual tactile policy learning. So, and in Manifold, so we introduced a wide range of contact-rich manipulation tasks here. For example, the USB insertion, power insertion, and we also have some kind of like manipulation tasks where the robot has to work in environments where the vision is not reliable. For example, sorting the object in the dim lighting environment, or do the object retrievals in the enclosed container where the external vision is occluded. And to capture the tactile feedback, so we use like the vision-based tactile sensors or like the chair size sensor that I introduced earlier. So this sensor can provide both the three-dimensional shear force as well as the contact geometries or the texture sensing on the sensor skin surface. And because we want to focus our benchmark on the simulation environment, so here we employed like the tactile simulator developed by NVIDIA. Is like a TechSL here, and the simulator can also provide the similar tactile information that we can observe like from the physical device here. For example, here you can see the simulator, the tactile sensor in the simulation can also capture the contact geometries or the texture of the object, and it can also offer like the three-dimensional force interaction. And here, so we evaluate the robot learning performance in the three different like sensing configuration here. For example, here we have the vision only, and we have like vision and tactile RGB, and we have the vision and the tactile force fields here. And actually the tactile RGB here is just the raw tactile images that we capture from the sensor. It can provide the contact geometries of the of the objects here, and the tactile force fields is the force field that we get from the shear of the depth information here. And here we show like trees like a representative task here. As we can see here, we evaluate under the gear assembly for the vision only. So when we try to insert the gear base into the hole here, actually like there is some occlusions from the wrist camera that the robot can observe. Actually, it's failed to achieve the task. However, when we integrate with the tactile force field here, so the robot can achieve the task more easily. And here, so we also like showcase the performance of the robot in the bones sorting task here. Actually, in the environment we have like the two balls, the golf ball and a table tennis ball that appear to be like similar in the shape and size. And actually, we also want the robot to sort the golf ball instead of the table tennis ball in the dim environment. And as you can see here, so when the robot do with the vision only policies, so actually the robot usually confused like which one is the correct ball, and actually here's the performance when we compare like a different like sensing modalities. And it showed that so when complement the vision feedback with the tactile sensing, the performance usually achieve like the combination of vision and tactile information can achieve like a better performance compared to the vision only policies. And to validate like the results that we observe in the simulation, here we compare the vision only policies that incorporate the tactile feedback on the physical real world experiment. So first for the gear assembly test, as you can see on the left, like the vision only policy usually fail to properly align the gear during the insertion process. So in contrast, with the tactile feedback integrated over there, so the robot can detect misalignment during like the force at the fingertip, and it can adjust and adapt its action, and finally it can like successfully complete the task. And so next we want to evaluate for the bulb installation task as well. Similarly with the vision only policies, so we observe further cases such as like under tightenings when the robot doesn't achieve enough rotation here, or like we observe like the over tightenings when the robot tries to provide more rotation, even though like the bulb has already like secured. And however, with the tactile feedback here, because we can sense the interaction force at the fingertip, the robot can perceive the slip between the bulb and the fingertip when the bulb already secured to like provide enough snug fit installation of the bulb inside the socket. And finally, for the ball like sorting task here, we have the golf ball and the table tennis ball, and we want the robot to sort the ball to the designated balls. And for the vision only policy that operated in a dim lighting environment, you can see that the task here that we want the robot to move the table tennis ball into like the blue ball here, and the golf ball into the orange ball here. But we can see that like the robot usually like fail to sort the correct ball. When you see here it's moved the table tennis ball to the orange one, it's like it fails like a sorting. So however, like you can see over there, like with the tactile feedback, so the robot can achieve the task very reliably. And so in summary, so in this session, so we have seen so how soft-data sensing combined with control and learning framework can enable safer and more reliable robotic system. Like before wrapping up my talk, so I would like to show a couple of examples. So how my research can be extended to other robotic platforms, such as like aerials or mobile system. So here, Can
you please help understand the takeaway from the last section, in the sense that you have three policy frameworks with three different performance benchmarks across the different like types of jobs like bulb sorting or sorting and bulb fixing, and there's one more. So I'm just trying to reconcile that with like you're creating a general purpose motion or general purpose learning. Like how does it reconcile? I'm trying to get the takeaways from it.
So yeah, and yeah, I forgot to mention like the takeaway from here is that so actually for some kind of like gear assembly task or in translation here, usually each task will usually requires like understanding of the interaction force between, like for example the bulb here and the socket, for example, or the gear here and the base. And in this task we observe that usually the tactile interacting with the tactile force fields enable the robot to perform to get a better performance compared to the vision only. However, the tactile RGB here seems to be not very related to the task itself. So usually when even though tactile RGB is still the tactile information, however, when we integrate the tactile information that is not so relevant to the task, so the performance is not necessarily achieve the better performance compared to vision only. However, as you can see here for the bond sorting task, because the robot needs to know the texture of the bonds, right, so that it can achieve like the precise sorting. So in the task we see that, so with the tactile RGB that can capture the texture of the objects. So usually combining the vision with the tactile RGB achieve like make the robot achieve better performance compared to the vision only and the vision tactile force field itself. Yeah.
What is the thinking process between choosing these categories, these kinds of tasks?
Can you say it again?
What is the thinking process behind choosing these types of tasks?
Yeah.
The assembly, exploration, and storing tasks.
Yeah, so actually we want to like a diverse, like different contact risk manipulation tasks where the robot has to rely both on the force or on the texture to examine so which tactile modality contribute better to the task that we choose. So that's why we want to diverse the task that we selected. Yeah.
You mentioned some gaps on being able to evaluate, and ultimately the final evaluation is based on success. Was any of this instrumentalized, or did you guys were just like watching it both in sim and in reality and evaluating whether it completed the task successfully? Meaning, did you develop a way to evaluate it, or is it mostly like success based?
That's a very good question. So actually, I think like nowadays we have like several common like metrics that we use for the robot evaluation, and it turns out that like the success rate is still like the common metrics that people use for the evaluation. And another thing is that we can try for measure the performance between like sensing version is like the completion time, or like how long does it take to like achieve a task. And I think like such kind of metric is kind of popular now.
And it's manually evaluating, hey, did it complete it or not?
Can you see?
So there, and you guys are in the loop by watching it complete the task and then say, hey, this.
Yeah, it is like actually for the real world experiment, we need the human to just like the task success. However, for the simulation here, so we have like the matrix or like the function that can automatically like evaluate the task success here. Yeah.
For the sensors between TAC-RGB and TAC-FF, is that the same sensor, and then can you...
Yeah, it's the same sensor, but we can obtain like both information simultaneously.
Okay,
Yeah.
cool.
Yeah.
I'm thinking about the light bulb task. Can't you infer if the light bulb is at the like torqued or snug from the motor torques? Do you need to have?
Oh, that's a very good question. I think the robot like if we use the torque like at the wrist of the robot, right? Actually, we can also do the same thing, but here so we want to. Yeah, but here we want to more focus on like the sensor at the fingertip. So that's why we haven't examined like carefully. Yeah, the sensor at the wrist of the robot.
Is the idea that given the same amount of data you can achieve it's more data efficient, or is it that snug is really subtle that you might not be able to see it with the motor?
Yeah, that's a very good point. I think that also like depends on the resolution of the wrist like sensor here, and actually if we can complement like multiple tactile sources from different devices, I think it can enhance like the performance further. Yeah. Yeah, and for the last part here, so I would like to like quickly like show a couple examples of like how like a soft like technologies like soft robotic technology can be like combined with the control framework for the robotic platforms like such as aerials or the mobile system here. For example, here we want to highlight the combination of the soft robotic components for like for the propellers here with like the reactive control to like reduce the impact and effective line recovery. As you can see, when the soft propellers like collide with obstacles, like it can because it's soft, so that's why it can recover from the impact, and actually from that by combining with the reactive control, it can enable like effective flight recovery here.
So
And
does the motor like slow down suddenly when it detects the impact?
no, actually, because like here we have the nonos with like the soft materials, so that's why when it collides, it's not slowing down at all.
Oh, okay.
But actually, the how to say like the propeller here will bend, but it actually can recover to original state upon the impact. And here's like we demonstrate how data sensing can improve like the system performance of like mobile platforms for contact-rich manipulation tasks here beyond like the tabletop manipulation that we introduced earlier. So in this setup, like we integrate a robotic arm on like with like tactile fingers here, like on the waterbed robot. So to enable like simultaneous locomotion and manipulation in the real world environments. And we also like develop a hierarchical controller platform. So for this kind of like manipulation task. So at the high levels, like we use like real world human demonstration, like for emulation learning for context-aware trajectories. And at the lower level, so the trajectory is executed by a low-level policy trained using like large-scale reinforcement learning in simulation. And we validate this approach on like several tasks, such as back-and-forth insertion, valve operation, or dedicated facial object operation. And we observe that with the stand-up touch at the fingertip here, yeah, it's still like the system like achieves a better performance compared to the system that only have the vision modality alone. And so far, like I have presented like my research on like self-tactile bodies and multimodal learning and control. So looking ahead, like my research vision is to develop like an embodied intelligence system that can operate safely and reliably in the real world environment. So I'm particularly interested in applications such as robotic assistance in the home environment, precision manufacturing, and agriculture harvesting. So in these scenarios, so I believe that self-robot bodies, tactile sensing, and advanced intelligence are essentials for safe and reliable operation. And in the short terms, like my focus on hardware side is to advance the software sensing for full like robot bodies and human-like dexterous hands. So a key challenge in scaling tactile sensing is to how to process the dense tactile signals efficiently and in the parallels. So, and on the learning side over there, so I plan to continue exploring how effectively incorporate tactile feedback into the control and learning frameworks together with other modalities, such as like a vision and the language. And so finally, I would like to thank my collaborators, mentors, and students who have contributed to this work. And I would like to thank like reference agencies and institutions for their support. And actually, so because I'll be like assistant professor in like the University of Nebraska Lincoln, so I have like a several PhD position available. So if you are interested, so please scan the QR code for there to learn more about the position. Thank you so much for your attention, and that's it for my presentation today. Yeah.
Thank you for the amazing talk and amazing work. So long term, you suggested like full body contact sensing, and gel site and camera based sensors are typically quite expensive for and what they are. And there are works from other labs, like back in the day from Sang Kim's lab, where they do like silicon and liquid metal based sensors. And they also provide like, they provide torsion, they provide stretch, they provide force. What are your thoughts on which would be a better sensing technology, a camera-based one or a capacitive or like liquid metal?
Yeah, I think that's a very good question. I think like in the long term, like it doesn't matter like which sensing principle that we use, but I think it's the time for us to focus more on like how we can process the tactile information effectively, because like now so we want to process the tactile information from the entire robot body. So actually how we can like process it effectively, I think is like more important research question. As one of the direction that we can go is that we can use like neuromorphic sensings, which is quite similar to how like our human bodies process the tactile information. So actually, so for now, our robot body, it doesn't process the tactile information like every time, like every moment, and actually it only process the tactile information when there is the spike in the mechanoreceptors. Receptors, and we want to like mimic that behavior for the robot here, so that it can more like effectively process that information. And I think it doesn't matter with what kind of like a sensing principle that we're gonna use, but actually the sensing principle that can provide like the reliable and durable like hardware sensors could have some advantage in this kind of field. Yeah.
For the cylinder-looking sensor that goes on the arm, I'm trying to visualize and maybe think about the applications of that. Wouldn't you, if the application is not bumping into someone, wouldn't you want to avoid the policy failure in the first place instead of worrying about bumping? Like, I'm not going to bump someone. I don't need to feel them before I bump them. I'm not going to bump them in the first place.
That's a very good question, but I mean like there's still scenarios that actually the vision or like alone doesn't enough to like make like the collision avoidance effective. For example, when you work in the daily environments, there is some objects like the glass or like some shiny objects that can make like, the vision only confused, and it can make the collision avoidance before the contact doesn't work very well. And in that time, I still do think that we still need like the contact feedback, so we can better like handle some kind of uncertainties in the daily life environments.
So it's when the policy fails it kicks in.
Policy.
When you have like a policy failure, it's gonna back up.
I think that's the good part, but I think it's still good to add up like more like sensing modality there, and I think that could be come from different like research interest and research flavor. But for me, I still do think that like adding more like tactile feedback is still crucial. Yeah.
How do you think of tactile foundation models?
Oh, that's a very good question. And I think like tactile foundation model is something that we also want to achieve in the future, but actually there's like several challenges here. So the first thing is how we can like collect the data sets for tactile foundation models. And as you can see nowadays, so each research lab, they have their own like research, they have their own tactile hardware, right, that comes from like different sensing principles, and each sensor also provides like different tactile information that we don't have like consensus yet on which tactile information is important. So I think that's enable like several challenges to collect like the tactile data set here. But I think like tactile foundation model is still important, but there's still several challenges that we need to resolve before we can get there. Yeah.
What do you think of the debate between getting force feedback from tactile versus just getting touch, no touch, and then force feedback from back drivability and stuff like that? Like how there are like also studies that suggest we get our force feedback from our joints and not from our skin.
Yep.
and skin is just for like touch or like very steep pressure or temperature. So as we have more backdrivable like humanoid hands, that gives us more like force feedback.
Yeah, I think it's like actually it can come from several layers. For example, for the force feedback at the joint level, maybe we can leverage that for the lower level controller. But for like some kind of like force feedback that we can obtain from the fingertip, maybe we can use that to infer more like effective, like high level perception or high level like controller before we pass the control command to the low layer. And at the lower level, maybe we can leverage like the feedback from the force feedback from the joint, so that we can achieve like precise execution of the command from the higher level controller. Yeah.
And do you think we need like forces in just newtons or like pressures are better?
I think it's like a precise force measurement. I think it's not that kind of necessary. Maybe we just need to like roughly estimate how much like the robot comes into contact with the object, but we don't need like precise force measurement. Yeah. Yeah.
How important is resolution in these sort of tactile sensors? Could you not just put like a bunch of load cells over the link with a sheet over it?
You mean like
Yeah, like have some small load cells and then just put a sheet of metal over it so that you can identify where exactly the point of contact is based on the load cells?
Oh, actually, yeah, we can do that. But actually, if we want to do that and we achieve like the spatial resolution that we achieve right now for this tactile link, I think we need a lot of load cells. And yeah, actually, if we put a load cell there, I think it will increase the complexity of the systems. So even though, like for our system here, we only need one camera, but I think it can achieve like very fine spatial resolution for the contact detection. And we don't need a lot of hardware device for the iteration at all. Yeah.
So I said that you can use in precision manufacturing. I was wondering how long it will take this technology to help like in fashion there's pattern designing to replace like the human parts.
Oh, I think that's a very good question, and actually, like, I'm not quite sure about like the answer yet. And actually, I think nowadays we see lots of like demonstration videos where the robot can, do assembly with like a subtle, like parts. But I still do think that there's still lots of challenges that we still observe here. Actually, when we want to achieve this kind of like precision manufacturing. With the same level with the humans, I don't think that it's just about the problem of the intelligence, but about the problems of the hardware, where like the hands of the robot, how we can enable the robot hand to achieve the same level of human dexterity. I think is the one challenge, and another challenge is how we can enable like the robot brain to process those kind of tactile information. I think it's still far away that we can achieve such kind of a capability, but I'm not sure about the answer yet.
We collect egocentric data in hospitals, and one of the things that we're looking to is to branch out into actually collecting human contact data.
Yeah.
I was wondering if you had any thoughts on how much can we actually conquer safety if we aren't collecting human contact data and intersecting that with tactile.
Yeah, I think that's a very good question. Yeah, I learned that there are several words we try to infer like contact interaction of the human hands, the object using the vision alone. But I still do think that to collect like the accurate the contact data, we need the device to do that. And I think nowadays like the Yumi portable device could be some other way to enable it to achieve that kind of contact information from a data set.
Cool.
Yeah.
So, thanks for the talk. You were saying something about the tactile foundation model. I have a question because the different tactile sensors across the different embodiments. And when trying to do this tactile foundation model, how can we make sure it's going to work on all the embodiments with different sensors? Because different type of tactile sensors, like precision manufacture is different, domestic distance is different, and I think that's really different. So
That's exactly what I mentioned as the current challenge. And I think it's like one of the way that we can though to solve it is we should come up with like the unified tactile representation. Actually, we can have like one representation that is trained like across different embodiments of the tactile sensors with across different tactile information. And once we have like the unified tactile representation, I think at that time we can scale up the data set for tactile foundation model.
Isn't the gathering the data set itself is a big challenge?
Yeah, I think that's a good big challenge, and I think that need like the joint efforts from like different research.
Yeah, I want to follow up on the data cloud, the tactile cloud question, and I feel like that's a really hot topic right now. Like people trying to add the human tactile data to on top of egocentric videos, right? And now it's usually using the conventional tactile technology. You mentioned at the very beginning, right? And it's obviously have a lot of problems right now, and the accuracy, the noise is not very good. I heard the major challenge comes from the tactile when you test that soft tissue that affects its like signal accuracy a lot. So do you think the technology you use specifically can help with that, or you think there are like basically what's your like vision for this? How we're gonna solve this problem?
Oh, I think that's a very good question, and actually I'm still wondering about that every night and every day. And actually I don't think I have like the good answer for that yet. But actually that one is like exactly that what we want to do in like my new research group. And I still do think that like in recent years there is no like a new technology to enable like the raw state of touch. We have capacitive, we have like inductive sensing, real receptive, visible or optical way data sensing. And I think like each have their own problems, but how we can leverage it, how we can advance, and we can we should try our best to solve like the problems we have in such kind of device. And I think so what difference like from now from before that we have like the machine learning. And I think with the machine learning we can somehow like arrest better some problem that we see in the signals that we cannot solve that before. But I don't have like the good answer for that one yet.
There's no perfect hardware technology.
I think for now it's not yet.
Well, what's the major challenge to make it work on soft materials? I'm like know very little about hardware. Like, what's the specific challenge?
I think the challenge should be like the durability and the compatibility between like the electronics and the soft skin here, right? Because now we have the soft skin, we have the electronics for like sensing components, how we can integrate that effectively. I think that's one of the challenge. So that's why we want to use the visibility tactile sensor here, because we don't need the interface between the hard and the soft layer, between the electronics and the soft skins.
So what are the challenges if you apply this type of vision-based tactile technology to data cloud?
I think one of the challenges should be the shape. Because like nowadays, like I think like camera, they have a little bit like big size, and because the data cloud, maybe somehow we need to optimize the space that we can put the camera inside the glove here. Actually nowadays we still have like some kind of like more scale camera devices, but I still think like customize the vision by data sensors for like the scale of the cloth, I think it's still challenging. But I think like I still want to try that. Yeah.
Should it still be like camera for every digit and every link, or should it be more like some other sensing? Because then if you have for every link a camera, that becomes a lot of data to process downstream. That's
so I'm thinking here. So actually, for the tactile fingertips, maybe I would like to use like a visible data sensor here, because it can provide both like the force interaction data as well as like the texture, right? And usually the fingertips is like the areas that the robot I think need to interact with the external environment most. And for example, for the PAM or like for other like for languages, I think we can go for like a different sensing principles, like the capacitive sensing, as you may see from like Bing Hao from Columbia University. He has like very nice tactile sensor array for that. I think we can leverage that for other areas of the arms. And but when we do that, I think we still have the challenge how we can combine like a multimodal sensor data from multiple sensing principles. But I think that's good for investigating. Yeah.
What are like general issues with capacitive sensing with compared to cameras?
I think it's like the issues with the capacitive sensing is like the calibration, like the signal processing, for example, is quite challenging to like calibrate for the capacitive sensing, and we still have some the electronic circuit interface with the environment, so we may have some concern regarding the durability of the sensor device as well. And in the long term, maybe there's some degradation in the tactile signals. It might limit like its applicability for like real world uses over the long term. But if we just do that for research purpose, I think that's good enough. But for the real world uses, I think there's still several challenges for the capacitive sensing. Yeah.
Sorry, on the same topic, like Tesla, Optimus, and Boston Dynamics, they chose electrical vision-based sensors over optical-based sensors. Is there, because of low latency and other things, is there like is there a reason why they chose the electrical signal tactile sensing over optical sensing?
Can you say that again?
Sorry, I'm saying on your answer on tactile versus electrical sensors.
Yeah.
Tesla, Optimus, and Boston Dynamics, they chose the latter one. So because they said it's more low latency compared to the vision-based sensors.
Oh, I think that's a very good one. Yeah, but I also heard like one guy from the tactile team in like Boston Dynamics does. So I heard like they are using magnetic-based sensing principle, I guess. But the problem is that so actually they can have like the lower latencies. But the problem they observe right now is that so actually when they try to repeat the interaction with the external objects and the sensing signals, they return different. And because each of the same actions, but they return the different sensing signals, actually that's make like the learning process is very difficult. And the guy from the team told that actually they face challenge like that, and actually the robot learning team cannot do anything about that because the signal return from the sensing is not reliable. And I think one of the points that the vision-based tactile sensor can solve here, actually it can return very reliable signal over like the repetitive actions. Yeah.
Question. So if you were about to start a robotics startup, which niche would you pick? And if you don't think it's the right time, how long would you wait till what milestone come up?
Very difficult question. I think like if you want to do this startup, maybe for now maybe I will start on like the robotic hands, like the Dexterous hand with like tactile sensors integrated on that, and any like kind of device associated with the Dexterous hand as well to collect the data set for the that kind of device.
So you think like the biggest problem in robotics is the data problem?
I think so. I think so. For example, nowadays, like how we can collect the correct data for the robot data, I think is still a challenge. And if we can scale up the data, I think it's very good.
So how are we gonna solve that?
No, actually, I think like the robot data is one of the problem. I think another problem is how we can have the correct hardware for the robot as well. Yeah. Maybe we can talk later. Yeah.
So, just a hot take. What's your take on the 1X hand which you just got demoed like 2 days ago?
Sorry.
What's your hot take on the 1X the Dexterous hand demo which they did?
I think that hand is super good. I think it's like the good one is that they can enable the compliant like a motion of the hand. Yeah, and it can achieve very agile because it uses like tender-driven like mechanism, right? And I think that's a lot of problem about the compliance, about like the speed, the strength of the robotic hands. I think that this could be the one of good mechanism that we can go.
I have a similar part. I'm doing a startup working on Dexterous hands, and also we build some sort of human wearable device to collect human data with tactile, then match our Dexterous hand. So I'd love to talk with you more about that, and if you have time.
Sure, we can talk later. After this.
Like as far as I know, like the tactile information is pretty hard to be utilized for the other algorithms, other training. So like I was wondering like if you have tried like using the tactile informations to train for the other algorithms to make it work well for the out of distribution states.
Yeah, that's very good point. And I think like integrating the feedback into the current algorithms and into like some learning control framework nowadays. I think there's still a lot of things that we can we have to solve that, because like in the nature, right, the vision and the tactile sensing, they don't come from like a similar time step, and actually integrating both information into the same level may not be the correct way to go. But I think it's like we can integrate them into like the hierarchical levels. For example, at the higher level like perception, we can leverage the vision information or some tactile performance or some tactile like high-level perception for the high-level control layer, and from the high-level control layer, it can generate the commands that, and at the lower level, for example, here we have like several layers, right? And for like the safety layer, for the lowest level layer that requires like the reflected action of the hand or of something, we can leverage the tactile sensing there. For some kind of reflective behavior or some faster responsive of the action based on the tactile feedback. So actually we need like the hierarchical level rather than just like use the two information, the vision and tactile information at the same level. I think it's not that effective.
Any other hot questions? Let's give another big round of applause to our great speakers. So, a few announcements of future Saturday Robotics Reading Club events. Next Thursday, July 16th, is Saturday Robotics is happy to collaborate with Autonomous, the conference on physical AI, and I'm happy to be invited as a speaker and a panel moderator with Foundry Robotics and Faraday Future on physical AI on the production line. And next Friday, July 17th, Embodied Metal Hackathon. I'm happy to be invited as a judge of this hackathon, and it's gonna last until Sunday. And next Saturday, July 18th, it is our reading club number 18. The topic will be, there were two keynote speakers. First is latent all you need for world action models. So we will have a overview on many kinds of world action models and recent papers on WAMs. And the second keynote speaker on causal world models, Professor Bi-Wei Huang from UCSD, and she is also our old guest from our reading club number 13 with the Human Eagle. So she raised 20 million on her new startup, and she has maybe some more interesting hot takes to share. And this is July 18th. And July 22, Saturday Robotics is going to be in Los Angeles for SIGGRAPH conference. For those, if you're research on computer graphics and simulation, and I'll be hosting an official conference, SIGGRAPH conference approved Birds of Feather event in the main conference room in Los Angeles Convention Center in on July 22, Wednesday afternoon, 3:30 p.m. And then July 25, Saturday, it is our reading club number 20. This reading club is gonna talk about the agentic robotics models. So I'm gonna invite the author of Empire, recently NVIDIA's new paper Empire, and Haru Xue from UC Berkeley. It is about the agentic robotics, and also he's gonna share some previous related work. CapEx collaborated with Ken Goldberg and UC Berkeley. And so this event will be in Mountain View, Samsung Research. And August 1st I will invite the reading club will be Yanren Wang from UC Berkeley, and he is going to share the recently released, I think a few weeks ago, the new paper Vision Language Kinematics, VLK. This is a new work for egocentric images, language command, and robot compatible kinematic trajectories. And August 8, I'm happy to invite Hao Yinyu from UC Berkeley on his new work, ODE World, a continuous predictive architecture via physical time flow. So this is a novel approach that learns a continuous latent velocity field operating in physical time. And August 15th, I'm gonna have probably but not yet confirmed Lyndon Gao and Jason Ma from Data Robotics for a panel, and probably Tan Jie from Google DeepMind. And this is co-host with my U Chicago alumni, an investor from INC, but this is not confirmed yet, but it is probably I'm gonna put up the Luma page soon. So before our open floor discussion, as a tradition, let's take two group photos, one egocentric, exocentric actually, another a third person's view. And after that, you're free to enjoy some remaining strawberries and also enjoy the good view of the San Francisco city. So let's first do a exocentric. Let's do together.